you all for coming today to our first in-person speaker of the spring semester. I'm gonna let Casey introduce the speaker, but I appreciate y'all being here. Morning, everyone. We have Dr. Jason Fridley today. He's a professor of biological sciences here at Clemson University. His research focuses on force dynamics in relation to global change drivers and invasive species, involving plant physiology, microbial ecology, and field-based sensor techniques. He moved to Clemson from Syracuse University in 2022. Join me in welcoming Dr.
Thank you all very much for coming me out. This is a real treat for me to talk to my colleagues and students across campus and give me an opportunity to talk about some work that's now closer to home. It's great to be able to say that. Thanks to Casey and Frank for help organizing this. So we do plant ecology in my lab across campus in Jordan Hall. We're really interested in forest ecology, and we have a research program in invasive species biology. I'm not going to talk about that today. Instead, I'm going to take the opportunity to give you some vignettes of the type of research we're doing on native communities in the Southern Appalachians, and in particularly Great Smoky Mountains National Park, where I've had great joy of working for the past 20 years or so off and on. I know you've had several talks about the Smokies in the last 6 months or so, so this is going to hopefully complement what some of the other speakers have talked about. And I want to emphasize that the reason why there are so many of us working in the Smokies, and many of you may know this, is it's probably the most diverse place in North America for studying, particularly woody plants. People have focused on it for a really long time. This is a species area curve. So this is log scale of square kilometers on the x-axis, and this is the number of plant taxa on the y-axis. The Smokies are not the largest national park by any means. It's not even the largest national park in the Eastern United States. Technically, it's bigger, but it is the most diverse. Way more diverse than all of the Western parks. It's probably many of them combined, I would guess. You know where the Smokies is. It's about 2 hours from us, nestled on the border of North Carolina and Tennessee. And one of the reasons it's so diverse, it's undeniable, is its relief. It is a complex topography. And at least since the work of a classic paper by ecologist Robert Whitaker as part of his dissertation back in the 1950s, he was actually originally studying insects and got so obsessed over the vegetation patterns, he ended up working on vegetation for most of the rest of his career, in addition to many other things. But this is the classic Whitaker diagram. Many of you may have seen this. It's even in introductory ecology texts. And the idea is there are two gradients that together create this incredible ensemble of niches for different species that create this really complicated environmental template that no one species can be adapted to all these places. Okay? So he called these axes an elevation axis, which of course is a major climate variance at very small scales, and an exposure axis. And what he meant by exposure, and he talked about it in terms of mostly water, is differentiating between really protected places in the mountains, hollers or coves or canyons, as opposed to fairly nearby places, but very exposed up on ridges. Okay, and you know these places, these are areas where there's less tree density, the tree species are very different, it tends to be a more xeric community, and historically, of course, the fire frequencies were a lot higher. And so this template of exposure and elevation gradient plays out across the park. It's more dramatic at low elevations than it is at high elevations. So this particular figure is going to form a template for a lot of the data that I'll show you. And I'm going to change what the x-axis is from time to time because unlike elevation, exposure isn't a real thing. It's something that we've constructed. And there are a lot of different ways we can measure that in landscapes, right? So sometimes I'll say it's distance from the stream. Sometimes I'll say it's radiation load, and I'll get even more complicated at the end, and I'll combine a couple of those things. But this is the template I want you to keep in mind. And of course, even though Whitaker's paper, you might know it because it kind of proved the continuum concept in plant ecology, that there are no defined boundaries in plant communities most of the time. Species have individual distributions. But even Whitaker presented it as a mosaic of forest types. It's really hard to think about, say 50 different species of woody plants distributed over that individually. He even did it in kind of a 3D scape, looking at Mount LeConte here. And today, of course, there are many dedicated staff for the park and the National Park Service that build new vegetation classifications and map them over the landscape for management purposes, right? And there's a very active group that does that in the Smokies. But I put this here to show you how complicated it is in terms of relief. This is just like the first level of forest types. If you look at all the defined forest types of the Southern Appalachians, and particularly the Smokies, there's many, many different forms, and they all exist within a very dissected, very fine scale landscape. So topography is a lot of what goes on in terms of what we think of ecological dynamics in the Southern Appalachians. And of course, the big question in front of us is, what does that mean for the future of these communities, plant and animal communities? And of course, people that are responsible for the stability and maintenance of these communities are really interested in. Elevation is not changing, not at a scale that we care about. And exposure, we don't even quite know how to define it, much less what are the proximate environmental variables that actually drive that variation, right? So we need to figure out what these are, and then we need to decide how they're changing and project that forward. And then we need to figure out how do the organisms we care about respond to those new distributions, right? And I'll explain this map a little bit more later. This was actually developed by my student, Jordan Stark. One of the last things we did when I was at Syracuse. And this is a kind of micro scale map of thinking about temperature change in the Great Smoky Mountains that admits that this is a complicated place with highly stratified forests, that warming is not going to occur at the same rate everywhere. Okay? This is actually a map of 4 degrees Celsius warming of the region. So imagine this is maybe 50, 60 years from now. If the atmosphere warms 4 degrees, some places, particularly low elevation ridges, will warm almost 4 degrees, but most of the park probably won't. So I'll tell you a bit about what we're doing on that. And the kind of naive expectation that a lot of people who study montane ecosystems and climate change think about is if the atmosphere is warming, species will attempt to track that, and so they will move up mountains. So perhaps the vegetation, a naive expectation is everything's moving upwards. But also, if it's going to be drier, which is what seemingly the models are fairly consistent about, that maybe things will also want to move toward more mesic locations as well. So the net movement we're kind of expecting on these Whitaker diagrams is up and to the left. So I'll tell you just about kind of 3 main projects we've had ongoing, some a little older than others, but primarily what we're motivated in my lab is what factors drive forest structure and diversity across the Southern Appalachians, but particularly in the park where we have really good data and a lot of research support. Are these factors changing? How does that affect how we view changes in the past? And how can we use changes in the past to predict how the forests are going to change in the future? Okay, so let's start by talking about temperature. The easiest of the proximate factors to measure, I would argue. And when I started working in the Smokies as a postdoc, and it was my job to just kind of hike around and think about plants and temperature, we put together a kind of conceptual model of how temperature should be distributed in a forested, dissected terrain. And just a couple of things, you know that as we go up in elevation, we have less atmosphere, so the atmosphere cools. It's called the lapse rate. It's about 5 degrees Celsius per kilometer per 1,000 meters in the Smokies. But Cold air at night does really weird things. People say cold air moves like syrup across the landscape. It's dense, right? So actually it moves down slopes. And of course you can get cold air pooling in some topographic locations. Whereas during the day, it's less about how cold air moves, but how warm air moves up the slopes during the day. And of course, radiation has everything to do with that. In addition to, for a place to warm up, it actually has to dry out. So there's this latent heat effect as well. It has to do with moisture proximity. So a couple of us, this is 20 years ago now, when eye buttons were becoming all the rage, and if you don't know what an eye button is, it looks like a nickel. And back then it was about 20 bucks, and it would record temperature every hour for 6 to 8 months. And it was virtually indestructible. In fact, it was the only thing we found that we could reasonably keep hidden from bears in Great Smoky Mountains. So we bought about 120 of them and put them all over trees in the park. We chose a couple of different watersheds to focus on, and we created models of those watersheds. And this is temperature at about 1 meter off the ground. And then we had a validation data set so we could model temperature across those landscapes in these watersheds and then see whether or not we could predict temperature to a certain accuracy in other places in the park. This really was the best job I've ever had. And we focused on the idea of, we wanted to target really fine scale variation in temperature, right? We knew what it was like to be in Gatlinburg versus Bryson City. They have really good weather station data. But what did it mean to be on a trail in the Nolan Creek watershed and bushwhack from the stream a couple hundred meters to the top of the ridge and then back down again? And we put eye buttons at all of those locations. And that was kind of the structure of our data set. So what did we find? So each of these boxes is one transect. There's usually about 10 loggers. And for mean July minimum temperatures, so evening temperatures, we found this pretty remarkable and regular variation of a couple of degrees Celsius within a couple of 100 meters, which became this this is versus stream distance. And then maximum temperatures were pretty strongly related in some transects to annual radiation, which you can estimate from a GIS. So we put that in a model and we projected temperatures around the park at 1 meter. And of course you can do cool things with GIS and model, and you can look at this incredibly fine scale variation in temperature. And to give you a sense of kind of the scale we're talking about, within a kilometer or two, you can get a difference of about 4 degrees Celsius in summer or winter temperatures, which is about the mean difference in temperature between like St. Louis and New Orleans. So it's a massive small scale temperature effect that's not just elevation, right? And if you actually project this map onto those Whittaker diagrams, you can see here that indeed those low elevation ridges, so this is annual radiation, this is stream distance, you get basically the same pattern. Those low elevation ridges are way warmer than the protected areas, okay, across that elevation gradient. And here's the kicker. On average, the temperatures below the canopy are about 6 degrees Celsius in the summertime cooler than the weather station data. So organisms in the park, unless they live at the very top of the canopy, are not experiencing weather like weather stations are experiencing weather. So something to keep in mind when you're looking for data to model organisms' response to climate. And again, within 1 kilometer, you can get a substantial amount of variance. And there's this buffering effect, which is going to be important here in projecting these temperatures. So this is the model that went into the more recent effort by Jordan Stark, my student, to take kind of IPCC data and ensemble-based data of future climates and think about how it would affect the park. And so these maps are available online for Park Service. Anybody can have these. You'll note this is the high elevation band along the state border, right, where you warm the atmosphere at 4 degrees Celsius, but the spruce fir forests are warming only half that potentially. Again, those are cloud forests. So they're protected from radiation loading and they're always wet for now. They're always wet. So the real issue is whether or not these systems will dry out. That's the prediction of potential catastrophe. And Jordan actually went further and did a lot of species distribution modeling and compared the distribution of compared future distributions of different species with just a regional warming, ignoring all of this fine scale variation in temperatures versus a microclimate model warming. And I'll just show you the one result for tulip poplar, which of course is a lower elevation species and is very common around here, for example. This is kind of the projection if you use macroclimate is tulip poplar just kind of goes up the mountains and it doesn't have a whole lot of stable habitat. But if you use the microclimate distribution where particularly the areas around streams and coves will remain or be much less sensitive to change, there's much more stability of tulip poplar's habitat. So, and several other studies now worldwide have shown that if you consider microclimate in future distribution changes, there's much more stability, suggesting that some of these areas that, unless you actually go to the trouble of figuring out how microclimate is influenced by topography and forests, you don't understand that they can actually serve as these cryptic refugia potentially for species in a warming climate. And this is just kind of generalizes the results to the Whitaker diagrams. So again, 4 degrees of warming to the region. The most susceptible places are those low elevation ridges. The least susceptible places are the coves at high elevation because they're the wettest. And you summarize her results for over 150 species for which we had good distribution data. The most stable part of the park was these mid elevations, particularly in those cove locations. Okay. So this is kind of filtering the plant species distributions through those climate predictions and showing that, yes, even 2 degrees of change is enough to move a lot of species off the tops of the mountains because there are so many high elevation endemics. But there's a lot of stability potentially for mid elevation communities. But this is all driven by temperature because temperature is well mixed and is relatively easy and cheap to do an effort like this that requires 100 plus sensors. And I've been saying that everything has to do with whether or not you still have the water cycles that we have in the park today, right? So Whitaker's paper was not the only classic paper produced in the Smokies in the 1950s. Royal Shanks, a professor at the University of Tennessee, put up, he and his colleagues put up actually some of the first weather stations to go all the way up to the top of the mountains and all the way back down. They collected data for a number of different years. And this paper, he's actually summarizing this transect at different elevations in the Smokies relative to the understanding at the time of different habitat types and their distribution around the world in relation to moisture and temperature. And Shanks made the observation that particularly high elevations in the Smokies have climates that shouldn't exist. They're just way too wet for their temperatures. And of course, now we understand that that is not unusual for these incredible places in the world called cloud forests, places that live and get all of this orographic precipitation in places that are otherwise a little too warm. So the uniqueness of the Smokies may have everything to do with the fact that the highest elevations are getting absolutely inundated with rainfall. Some years, so we record over 3 meters of rainfall at the highest elevations. So this is probably some also massive moisture gradient in addition to temperature. How much? We don't know. Nobody's ever actually gone to the trouble of measuring that. And we also don't know what exactly is going on with moisture along the exposure gradient, even though that's what Whitaker always assumed that gradient was. These are plants adapted to wet conditions, and these are plants that can tolerate at least seasonal droughts, and often cases throughout history even more. But of course, the problem with soil moisture is you have to measure it in soil. And anytime you have to go in soil, you're subject to so many more fine scale processes that make this super noisy. The Smokies is no exception. The Smokies, some of the richest places in the park, as you may know, are these beautiful mid-elevation coves that have no soil. They're on boulder fields. If you try to stick a soil moisture probe in, you go, boom, it's just a boulder. And yet it's got some of the most water sensitive plants that we have in the Southern Appalachians, like Diphelia and a lot of these other big herbs, right? So this was a huge problem that we ignored for years. And then, so there's all kinds of problems with measuring it. You need a lot of probes. You need to do it over a lot of time. And it's unclear even how to model it particularly well. And of course, if you go to your favorite commercial source and try to buy the probes with the logger, I think the best you can do is about $150 these days for a good accuracy soil moisture meter. So enter incredible talents of Jordan Stark, who also did the work I just showed you on future predictions of distributions. And Jordan came to the lab with zero experience in electronics and decided to go for it. So she built these sensors based on this wonderful paper by James Mickley and colleagues at the University of Connecticut with the cheapest parts they could find and an incredible innovation in how we do this for long deployments, which is that this part right here is the real-time clock. The real-time clock is supported on this little tiny $1 battery. And that clock has an alarm that can turn off everything downstream of it for almost no power. So what that means is you have these incredible power savings, and anything you've got on this side of the logger has zero power drain for however long. So every hour this thing can wake up and for less than a second, turn on, take all the measurements, store the measurements in flash memory, and then go to sleep for another hour, right? So you can actually deploy these things for over a year, recording data every hour or 30 minutes. I'll say I have a lot more to say about these incredible machines, a lot of the work that Jordan did. If you have any questions, this man right here, Jeff Hamilton, is now the new director of our conveyor belt of sensor building in the lab, and is just about to put up a big, more detailed protocol. But you can build these with has 2 soil moisture probes at 2 depths plus a soil temperature probe for $20. So that's what Jordan did. This was during COVID. So maybe that was part of the motivation, a lot of lab time. And we got special permission from the park for actually Jordan to go to the park while people weren't supposed to be there. And she started deploying probes, focusing a lot on the Cosby area, but then also putting out a validation set of sensors. And she ended up putting out about 100 of these units, 2 depths. Again, we took a similar approach to how we put these out for modeling. And here's what our data set looks like. It's just absolutely incredible. So this is a 1.5 years worth of data. These are essentially the 100 records where you can see, of course, the storm events come in. They're color coded by elevation. Just an absolute, and this is all online if anybody wants to play around with it. So she summarized it and started to ask really simple questions. So we know that there's about 50% more rainfall on average that happens at the tops of the mountains than happens at the bottom. But actually, soil moisture on average, this is volumetric soil moisture, increases by almost 5 times from the bottom to the tops of the mountains. And the reason is that it's both supply and demand. There's more supply at the top, but there's less demand at the top because it's so much cooler because of cloud forest conditions, right? So you have the confluence of these 2 things, which means that soil moisture is actually, right now, so far as we know, probably the thing that varies the most in Great Smoky Mountains National Park on an elevation gradient. There's a little bit of topographic information in there that mostly has to do with slope. So essentially, if you're on a steep slope, the drainage is such that it's a little drier to the tune of about 700 meters in elevation difference. But it wasn't a dramatic effect, which really kind of shocked us. And in fact, Jordan threw a bunch of different proxies, GIS proxies, to see what was most correlated with soil moisture. And I mean, elevation was the big one. These are all the data throughout the year and a half, so of course it varies seasonally. Elevation was pretty good, slope is okay. Things like topographic convergence index, which is a very common GIS index for water index, not so much. Topographic position index, which is good for a lot of other things, not so much. We had a hard time actually finding a really clear topographic signal. I'm still not 100% convinced that's a real thing. Maybe we missed it somehow in the design of how we put out the probes. But if it is real, we do have a hypothesis as to why it's true. And if you've ever been in a cove forest in the Smokies, you know that these are huge plants, densely stacked, that the transpiration rate in those soils is probably incredible, particularly in the summertime. Whereas the ridge communities, there's a lower plant spacing. The trees, particularly on the tops of the ridges, are not as big as the ones further down the slope. And they're oftentimes conifers. It could be that the transpiration rate of those communities is so much lower than what we're seeing here that evens out soil moisture when you measure it with the roots right there, is that transpiration differences are balancing out the differences in that you'd expect from topography. So there's more demand by the trees in the coves than there are on the ridges. I have absolutely no idea if that's true. That's just a hypothesis that we're thinking about exploring. All right. So we talked about temperature and we talked about moisture, and temperature is the one that we're really confident has this incredible fine scale variation in the park that might help us explain a lot of why there's such great small scale turnover in plant communities. Moisture, there's definitely an elevation signal, and there's some other things going on that are still, I think, poorly explored. But then if we look at the predictions of just based on temperature of what's going to happen in the future, we have this idea that there's parts of this park in the Whitaker diagram that are probably more stable climatically than other parts of the park. And the part that I think is probably the least stable is the one that is the most subject to atmospheric change, and that is those low elevation ridges. Okay. The question is, do we have any other data to actually back this up, or are we just kind of predicting the future and have no validation data set whatsoever? Well, one of the other great things about working at the Smokies, in addition to having a huge amount of research support, is people that are interested in vegetation have been working there for 60, 70, 80 years. So we have this incredible data set available online. There's actually, if you go to the park data store, there's work that I and a number of other people have collated all these studies and put them on with soils data and all kinds of other things for you to explore. One, well, I'll tell you about a unique data set in a second, but if we think about going back over the last 100 years or so in the Smokies, how has the climate changed? Well, you might know that the Southern Appalachians are often described as part of the warming hole, which is this area of Eastern North America, particularly in the Southeast, where there has not been as dramatic climate change in the last couple of decades. I wish the weather records were better than what they are. We've got a lot of really good weather records at low elevations. We do not have very many good ones at high elevations. Even in the park, if anybody's ever been up Mount LeConte, you know that there's cabins up there that have been up there for the longest time. They actually, every day for, I think starting in the 60s, someone would wake up in the morning, reset the min-max thermometer and write on a calendar what the temperature was. And they saved those calendars, and we actually digitized them, and we have a record. I'm not sure if it's a good record, but we have a record of temperature for Mount LeConte. Even for Clingman's Dome, which has a very fancy weather station at the top, they don't collect data in the winter months for most things. So we actually have a really bad understanding of high elevation weather history in the park. But if we do some modeling, and a lot of people now model this at really fine scales, we can reconstruct what the climate history was. Here's two locations. That's where the visitor center is in Sugarlands outside of Gatlinburg. This is Clingman's Dome. It's just 12, 15 kilometers away. And this is from 1900. The warmest period in the Smokies is not now. It was actually during the Dust Bowl conditions of the 30s and 40s. And we're now kind of getting back up to that. And if we actually look at water balance, there's of course incredible variation. But if you look at something like the standardized Palmer Drought Index, it was a lot droughtier back in the early part of the 20th century than it is today. And in fact, the occurrence of droughts, they have happened, but they've been relatively rare. So the overall trend in climate for the Smokies is it's a little bit wetter now than it used to be, at least for something that's 100 years old. And that's actually true of much of the eastern United States. And you might know that we have a wetting trend. It's this a long-term trend. We don't think it's going to continue. And that's something that a lot of other people study. And the frequency of droughts is thought probably is going to go up. That's the general prediction with the warmer atmosphere, right? So we have a climate trend, but that's probably not the most important thing that's happened to park vegetation over the last 100 years. Probably the biggest is the way that the forests have been managed has been dramatically changed. You may know that right before it was made a national park in the mid-1930s, there was a race to cut every tree down. And they did a really good job. Only about 20% of the park right now is considered or some people call old growth. Some people say, well, just it wasn't subjected to large stand clearing disturbances. When it was made a park, that stopped. I mean, totally stopped. For the most part, it's been fire suppression. There have been some areas where there have been prescribed fires, particularly in the western side of the park, which was much more of a fire maintained, low elevation, piney landscape. There is even areas in the wetter part of the park where they've tried to do some prescribed. But for the most part, most areas of the park have not burned in a very long time. There's a fascinating pollution story in the Southern Appalachians you might be aware of. Industrial and coal fire power plants to the east, increased NOx gases, which increase ground level ozone, in addition to sulfate nitrogen deposition. EPA regulations have dramatically cleaned that up. It's one of the biggest shifts over the last 2 decades that have happened in the Southern Appalachians. So now some of the cleanest, if you're on Clayman's Dome today, it's about as clean as the air has been in your lifetime, my life. Pretty interesting. You know, it's the Eastern United States, mammals are what they are. So there's some areas where white-tailed deer are really bad. You may know that elk were introduced in the late 90s. I think their populations have stabilized, but boy, do I see them in very different places than they have been in the past. So that's something to keep an eye on. Of course, you might know that hogs are just as destructive there as they are here. And then the big one, if you're interested in vegetation, is it's just been insect and disease after insect and disease. You guys know all this. The last big one is emerald ash borer. We'll see what happens in the near future. I say all that because the Smokies has this incredible resource of during the Depression, a CCC team was tasked by head forester Frank Miller to actually do a systematic vegetation inventory of the entire park. At the time, the park was a little bit smaller because the area of Fontana hadn't been dammed yet. So it's a little bit smaller here, but Miller and his team, when I say systematic, I don't know if you've ever been in the backcountry in the Smokies, but can you imagine putting in a plot network of like equally spaced grids on the landscape? I mean, some of those slopes, you know, are like this. I'm not quite sure how they did that, but with some exceptions, it's pretty much a uniform distribution of sampling plots in the park. We've had the data for a really long time, and in the 80s, it was actually digitized by a student from University of Tennessee. It sat on floppy disks for a long time, and no one really did much with it. And then in the last 10 years or so, there's been a lot more interest. In particular, Julie Tuttle at UNC did her PhD dissertation, thinking about how communities have changed since Miller's time. Well, we've got 1,300 10-hectare plots of mostly woody species distributions. There's been a lot of work since the 1930s on vegetation, but it wasn't until relatively recently that we also had a, not uniform, but a more or less systematic sampling of the park's vegetation by the Park Service. And they did that because they were validating a vegetation map that they had established using aerial surveys. So we have 900 or so plots from not too long ago, so about 80 years of vegetation change across the park. So we're finally in a position where we can ask, how have communities changed across those gradients? And does that change indicate something regular or systematic or directional that we can use for thinking about future change? One thing, of course, in the Smokies you have to keep in mind when you think about forest change is that the disturbances have been massive in some areas and as low as anywhere in the eastern United States and others. So the red you're looking at here is where the corporations ended up doing the logging. So the vast majority of the central and west part of the park, and a little bit of the North Carolina side in particular in the eastern side. The purple is areas where they never got to, and which once the park was established, essentially there's been managed essentially as wilderness area, with some exceptions. So Charlotte Pyle in the 80s, working for the Park Service, actually did all the research to document all of this incredible work, which allowed us vegetation people to come in and say, okay, if we look at change here versus here, how much does disturbance history matter? And I think Margaret Woodbridge talked about this when she was here, maybe last semester. I missed her talk, but Margaret's working with us on this project. So I'll skip all the methods. If you're interested in species distribution model, let me know. But we've got 40 or 50 species that are abundant enough in both data sets to do some joint species distribution models. And essentially, we're allowing elevation and exposure plus disturbance history to inform how distributions have changed from the 1930s to today. And the cool thing about both those data sets is they have independent strata for the canopy and the understory. So we can ask, are there ways in which the understory has changed that might suggest future canopy composition as distinct from the canopy? All right, so just to kind of cut to the chase here. So here's a Southern Appalachian endemic, silverbill. This is a classic mesophytic species that you find in rich coves. It actually has a pretty wide distribution across the park. If we just think about 1930s places that were old growth, so had not been disturbed, and this is a general exposure index, so you can think about this as distance from stream. It's a little more complicated, but so here is the distribution centered in coves and mid-elevations of silverbill, the 1930s. And here's what the model suggests the distribution is today, right? So basically, the deeper the color, the greater the abundance, right? So silverbill has expanded essentially out from its most beloved habitats into more xeric habitats, and both high and low elevation. It's a bit more abundant than it used to be. The same is true, this is the canopy, same is true in the understory. Okay? So this species has succeeded into the canopy pretty well, but it's also recruiting into the understory really well. And you get essentially the same story, the same four panels in those parts of the Smokies that were harvested. So the secondary forests, they're even more abundant. So this suggests that there is some successional trend here. So it's kind of a mid-successional species, I would say. But the fact that the pattern is essentially the same in the secondary forest as it is in the old growth, there must be something else going on in addition to disturbance history. And most people would say that the process of mesification, which is simple, maybe complicated, depends on your perspective, is this idea that forests today are inhabited by species that we presume are much more moisture loving than they have been in the past, particularly in the understories. It probably has a lot to do with fire. It might have some to do with wetter forests today than we had 100 years ago. It might have to do with other processes, including traits of the species that make them more or less flammable. It's kind of a complicated story. But silverbill would be a classic species that we would include as a mesophyte, a species that's more abundant today than it was in the past. Maybe more abundant today than it ever has been in the Smokies, at least in recent times. Contrast that with the oaks. So every single oak species of which there are at least, 5 or 6 really common oaks in the park: white, scarlet, chestnut, red, black. Their canopy distributions have not changed that much, and now I'm showing you the change over the period. Okay, so each one of these is a difference. And if it's blue, it's less abundant than it was before. If it's gray, not much change. So these are long-lived canopy trees that they are slowly dying, and chestnut, for example, in xeric spots in the park. But there's not a whole lot of change of oaks in the canopy. But man, is there a massive change in the understory with essentially near or complete recruitment failure of every one of these species. Chestnut oak, of course, is a really prolific cedar, so you get a lot of chestnut oak seedlings, but you don't typically see them recruit into the bigger classes. Red oak is probably the most music of them, which you do still find some places. You can still find white oak and a couple other things, but compared to what they were 80 years ago, massive failure. And this is, by the way, kind of testing that hypothesis with the vital signs permanent plot network at the Smokies that staff are responsible for surveying every year. And this just kind of shows that the pockmarked examples are the places where there was really abundant oak and there now isn't, even in the understory. So plots are losing oaks. And this, of course, is something that's talked about all across the eastern United States. They're very true of the Smokies. If you look at traits of species and try to summarize these changes by drought tolerance indices or shade tolerance indices, you kind of get the story that you would expect from vesification. So even in old growth, so this is old growth, this is secondary, you get this increase, the blue is decrease in drought tolerance, particularly in those low elevation ridges, even more dramatic in secondary forests. And drought tolerance and shade tolerance are not perfectly, but almost inversely correlated in this group of plants. And so you've got this massive increase in shade tolerance as a bunch of species are recruiting into forests that are wetter and aren't burning anymore. And here's one result we got recently that, see if I can explain this. So this was really weird. So I'm not normally do community classifications. That's not my expertise. A lot of it is subjective and it's based on particular management needs. In this case, I used a community classification that was entirely objective. All you do is you give it the number of groups that you want, you feed it your vegetation data, and it picks back a classification of all of them. Okay. So what I did was for the canopy trees, I put in both data sets. Okay, both the old and the new data sets together. I said, all right, just classify all of these things. And I want, 5 different or 6 different categories. So it said, okay, it did. I didn't tell it what years they were. So what it gave me was, again, these are the Whitaker diagrams. Spruce fir was at the tops of the mountains. Goodness. Cove hardwoods were where they're supposed to be. This is mostly tulip tree, a little bit of hickory. So this is the Liriodendron coves at low elevations. Pine oak. And this is what I call oak chestnut. So this is where a lot of former chestnut distribution is. This is old growth from then and now. And these are secondary forests then and now. And there's a couple things to note here. One is that pine oak extent has increasingly gotten pushed down into the lower corners, so those low elevation ridges. The cove hardwoods has expanded, dramatically expanded in secondary forests. And the real kicker for me was one category that was defined only exists today. And it's this kind of maple poplar, so like red maple and Liriodendron, across this area that's like transitional between those fire-prone pine oak woodlands and the cove hardwoods. So there's a new vegetation in the Smokies today that didn't exist 80 years ago. And this particular spot was really interesting and probably the tension zone of the greatest change. It's even more dramatic in the understories where here's cove hardwoods that now essentially are everything. The cove hardwood thin bark species, mesophiles, have kind of conquered half of the low elevation Smokies. And the poor pine oak category is just shrunk into nearly nothing because none of those things are recruiting in the understory. And if you look at another trait like bark thickness, which is part of the way in which these species can resist fire once they get to a certain size. The biggest changes in bark thickness have been a decline in exactly those areas I was just talking about. This transition zone between low elevation forest, woodlands, dry, and the cove hardwoods. So I'm tempted to say what's going on is basically a fire frequency change here that has really affected these communities that probably did burn a lot in the past and have not burned for a really long time. Whereas both communities, of course, burned as well, but for the most part, my understanding is people had to set those fires. So you take the people out, you're not getting the fires here anymore. And here, these are the natural set fires that happen with lightning strikes, and they're just put out now, and they didn't use them. All right, so to summarize, right on time, summarize kind of what this analysis suggests about past change is the most stable communities in the park, particularly in old growth, are these kind of high elevation, or here's the compositional change, is these high elevation, more cove communities. Interestingly, the high elevations have not changed that much, even with fur-adelgid and hemlock loss and beech bark disease and pollution, which is bigger at high elevations. They're fairly stable composition. They have changed, but not as much as you'd think, except for the ridges, which is probably what a lot of the chestnut was. So no place is stable, but the farther up you go in elevation, the more stable they are. Low elevation, surely a lot of what's happened is succession after widespread disturbances, particularly in secondary forests. With the result that a lot of the canopy is way more diverse than it used to be, because those mid-successional species are now in the canopy in many places. Understory communities have lost a massive part of their diversity, in part because of this recruitment failure and due to succession. But there's a really clear change of many fewer species in the understory in these low elevation ridges and really high compositional change that has to do with the fact that those xeric species are being replaced with the mesophiles. So I'm not talking just about oaks. There's actually quite a few species in that group, like Nyssa, sourwood. All right. So to take a pause, just a couple of take-home points here. So microclimate is a big deal in the Smokies. We've got really good evidence for that now, especially in terms of temperature. This will probably play a big role in how these communities change in the future and whether or not they change. We understand what's going on with temperature better than moisture. So if you want to work on moisture, please come see me. We'll give you a bunch of sensors. You can hike all over the park and have as great a time as I did when I was postdoc. Stable forests aren't a thing. I don't think stable forests are a thing anywhere. They're not a thing in the Smokies, but they're more stable in areas that have probably been less impacted by long-term climate change because they were already pretty wet up there and they have yet to dry out. And in fact, if anything, they've gotten a little wetter than they used to be. But the forests that are unlike anything that used to be there before are these low elevation ridge forests. I think probably the dominant signal of change in the park is mesophication. That's just my opinion. A big question mark, because we don't really have good enough data yet to quantify it across all these canopy deaths, is tree mortality from invasive insects and diseases. The best studies that have been done so far, I think, are on hemlock, and those are still we're still getting a lot of information on that because everything died about 10 or 15 years ago. They did a lot of cool early studies on chestnut, but chestnut has such a huge niche that wherever they did the study, they got a different answer on what replaced chestnut. So that's still something that's a question mark. And then the communities, particularly in this story, are just less diverse at a local scale than they used to be because of these bullies, these mesophile thin bark species that outcompete these sun-requiring more xeric species in the understory that are not rescued by fire and they're not rescued by drought. Of course, in the future, that's the big question mark, because if there are more droughts in the future, the system is less resilient to that than it probably ever has been. You have a wetter, fire suppressed system that all of our drought tolerant species are not recruiting in. Faced with drought, it's anybody's call as to what the stability these forests are going to be in. And so we actually have a new research program that's more based on the physiology that's collaborative with Nishan Farrell, who's over in plant and environmental sciences, Patrick Martin, who is going to do the same work at Rocky Mountain National Park. And we're looking at hypotheses where in the Clemson experimental forest, we're going to be exposing a lot of these trees to drought and comparing their physiological responses to drought, but also what's going on chemically in the leaves, which can be kind of an early warning signal of whether or not these species are going to grow or survive as the intensity of drought increases. It's an approach called metabolomics, which many of you may know of. Looks at a lot of particularly like stress chemicals in the leaves. And we're going to connect that and try to connect it to demography, particularly these cases where growth becomes very minimal, but the trees are still alive. So it's kind of like an early warning signal. If we were to measure the same target chemicals in the natural populations, can we identify those that are still alive today, but may be on their way out because they're experiencing significant stress? And so we'll be doing a lot of work on that in the Smokies and the forest here this summer, and we've got positions open for some undergraduate help. So if you're in that boat or know of people, please have them get in touch with me. And it was a real pleasure talking to you all. There's a ton of people to thank, particularly a lot of graduate students have done, of course, as always, most of the hard work. And the staff at the Smokies are the best people to work with for research in plant ecology. I can't recommend them highly enough. For 30 years, I've had great relationships with these people, and they're the most dedicated to protecting this incredible resource. So I'll stop there, and I'm happy to take questions. Thank you.
Do you know if anyone's looking into the effects of herbivory on maybe like the musification, if there's a preference for those more xeric species like the oak, or if that's not playing at all?
Very great question. Yes, no, it's my answer. Mammalian disturbance was a big research topic in the Smokies for a long time, and that's changed. There was a lot of hog stuff, and there were exclosures for various things, hogs and deer. A lot of work in Cades Cove on deer. I'm unaware of people who are actively targeting that from a musification perspective, but boy, that would be so important. Do you know of anything? I mean, that's a wonderful research direction for sure.
I think I saw the controlled burns are slowly being brought back to the mountains. Are there any study areas that you'd want to do to see the effect of if that reverses musification?
Yeah. It's a great question. The answer is no. I have not really worked with the fire effects crew there, in part because the vast majority of their work is in the West, where I've never really worked before. But I think it has to be done. And I know they've asked questions like that as to whether or not whether we've reached an alternative stable state because of microclimate effects, that you can't get them to burn as much as they had in the past. And I know they've asked those questions in the Smokies. I'm not sure, I couldn't tell you whether or not there's a unique story to the Smokies in that. A lot of people include not they've asked those questions. So yeah, I would love to do more work on that in Smokies. I just haven't.
Yeah. So we did talk about disturbance, you talk about fire, but do you think the events like the wind throw will be more common in the future and that might affect the vegetation?
Yeah, great point. Yeah. Yes. So I have yet to see what was impacted by Helene. I know Catalucci and a couple other places were hit really hard. There was a tornado went through, big one, went through about 10 years ago on the more central western side of the park. And I had heard someone had actually done a study to see what was coming up there, but I hadn't heard more about that. Whether or not are they quantifying the extent to which wind disturbances are changing? It's a great question. That sounds to me like a remote sensing question, and as you may know, the center northern part of the Smokies is in the neon footprint, and they have hyperspectral LiDAR flights that you can definitely answer those questions. I haven't seen those papers, but I'll bet somebody's working on that. Great. Should I check if you was online or is there what you do?
Yeah.
Like it's a chat.
Money and time aside, what's like a dream research project you would do there?
I think I just put a backpack on and hike. What people do, but, yeah, so what, will happen before I retire, but I think what we're all trying to do is create a mechanistic model of forest change. And that requires linking physiological responses that are really well studied in plants to demographic ones. And by demographic, I mean these long-term birth death processes that you have to quantify if you want to make really good predictions. There's a lot of really complex models all over the world of that process. Probably the most famous one is from New England, Sortie. The amount of data you have to get to parameterize those things for one species is very daunting. The Smokies are the most diverse system. So what we're running up against is diversity versus accuracy in predictions. And is the inherent diversity of the system too much to make good predictions? Because there are just too many interacting objects. To say nothing about within species variation, which is also incredible in the system. So if I had unlimited time and money and had a big research program with 50 people, 100 people, we would start to make the connections between physiologically what's happening and how does that play out long-term with these demographic data sets. I think it's probably possible because there's a lot of really good permanent plot data from the Southern Appalachians and the forestry data set. And I think it's just a way of making connections between those demographic parameters and more mechanistic studies about water relations or metabolomics or what's going on in the roots. That's very expensive and requires a lot of people. That's what I like to do.
For the study on the Clemson experimental forest, which species are you focusing on there? Like, how do you select? Like, how are you selecting them?
So we have 6 species, partly because Nishan Fridley has a lot of not preliminary, but really good information on white and red oak and how they respond in these secondary metabolites to drought. We have to throw in red maple because red maple is such a big player today, and we had to throw in tulip tree because tulip tree is such a big player today. And then we added beech because of high elevations, that's something we need to think about. And then we didn't know really about it. We tried to squeeze in a 6th species, and that ended up what was going to be available for the nursery, and that ended up being scarlet oak. So we have those 6 species, 3 of which are oak. But Raymond is actually doing a bigger project with more species on just kind of drought traits. So for as many as 12, maybe more species, is to looking at rooting depth and isohydry, and some other things to get better idea. We won't be measuring those with the Smokies, we just don't have enough data. Yeah. Well, thank you very much. I appreciate your time.
Yeah.
Yeah.